So I want to do two examples just to help you get a head start on your homework this weekend. Before I do those, though, just real quick, after we talk through these couple of examples, you can definitely be doing in your handout packet 30 through 38. There's two problems at the end, 39 and 40, that you'll want to hold off on. And then, of course, your Chapter 2 homework 2 on WAMAP. Now, it's worth saying that there might be some of the more complicated questions that you get asked that you might just have some trouble with. Don't panic if that's the case, because we are going to continue with this topic on Tuesday, a little bit before we move on to new material. But definitely get a start on all this and try to do a lot of the problems in both of these assignments. So just a real quick review of the two calculator functions that we discussed. So we have normal CDF, and we have inverse norm. And so remember, what normal CDF does is if we give it z-scores, it is going to spit out to us a proportion of the normal curve that's between the z-scores we give it. And as for inverse norm, it essentially does the opposite. It allows us to give a proportion of the normal curve, and then it spits out z-scores. But the key is, whenever we give it a proportion, it's going to always assume that we're talking about the proportion of the normal curve to the left. So we got to remember that that's always what we need to be putting in to the inverse norm function. So let's do example 18 with this in mind. So it says find the z-scores that form the boundary for the middle 40% of the normal distribution. So as with all of these, we should start with a picture. So just give a quick sketch of a bell curve. All right in the middle here is 0. And so the idea is I'm looking for the z-scores that would give me the middle 40%. So I'm just going to, try to eyeball this best I can. Put little notches here. So I'm saying, what are these z-scores here so that this proportion is 40%, right? What is the low z-score and what is the high z-score that bounds that middle 40%, right? So if we want to know a z-score and we know a proportion, then that should be telling us to use inverse norm, right? Because if I go back to the little diagram here, inverse norm spits out z-scores. It will tell us z-scores. All right, so let's start with z-low. So z-low, we're saying that's going to be the inverse norm of something, okay? But what we have to remember is that the inverse norm always needs us to give the proportion to the left. So when I'm looking at this z-low here, it's nice that this is 40%, but what I really need to put in the inverse norm function is this green region over here. Okay, now we can figure that out. So first of all, if 40%'s in the middle, then that would mean that 60% is on the outsides, right? So if I talk about being split between here and here, put together, that's going to be 60%. So of course, just this green part on the left is going to be half of that, So that'll be 30%. And so that's what I'm going to put in to my inverse norm, is the proportion to the left of this low z-score. So my answer there, oops, I just lost it, sorry, give me 1 second. So my answer there is negative 0.524. Okay, and that seems reasonable, right? We know between negative 1 and 1 would be 68%, so negative 0.524 seems like a pretty reasonable lower bound for the middle 40%. Now, if you're thinking critically about finding the high z-score, you might realize that I really don't have to do any more work in order to figure it out. So to get the high z-score, if we just remember that the normal curve is perfectly symmetric, since I'm looking for the bounds on the middle 40%, the high z-score should just be 0.542. Right, just positive, the positive version of our previous answer. But it's worth noting, okay, how do I get that using the inverse norm? Well, I still have to give it the proportion to the left. So if there's 30% to the left here, and then plus the 40% in the middle, total I would have 70% below the high value, so I'd put 0.7 here. And of course that does give me positive 0.524. All right, but the main thing I want to do is show you an example where we actually apply this to some sort of a real-world situation. Okay, so we're looking at the average human gestation period, so the length of a pregnancy, we're told is 270 days with a standard deviation of 9 days and is approximately normally distributed if we assume spontaneous labor, so kind of a healthy pregnancy that kind of progresses on its own. So the fact that it's normally distributed means it's valid for me to draw a bell curve. Okay, so as I think about this question, I'll be thinking about the normal distribution. And they told us that the mean is 270 and that the standard deviation is 9. All right. Oops. So it asks me the question here, what is the probability that a randomly selected woman's gestation period will be between 261 and 279 days? Okay, so the obvious question is, where do 261 and 279 fall on here? Okay, so I've got these values. What's the probability of that? So I want to calculate my z-score for 261. So in this example, I want to show us a situation where we kind of apply this knowledge of the normal curve to a more real-world situation. So we're looking at human gestation here, so the length of a pregnancy, and we're told that the average is 270 days and that the standard deviation is 9 days and that length of pregnancy is approximately normally distributed if we assume spontaneous labor, so like a healthy pregnancy that's kind of going according kind of going textbook, and the woman goes into labor just spontaneously, that should be normally distributed. So with that knowledge, we know that any of these questions we want to answer, we can be thinking about this curve. So part A asks, what is the probability that a randomly selected woman's gestation period will be between 261 and 279 days? So when you're doing these story problems, what I want you to think about is, what are we being asked for? Well, clearly they ask us for a probability here. Okay, well, to answer a probability question about the normal curve, we're saying, okay, what are the chances of being between these two values? So if I can figure out what percentage of the curve is taken up between those two values, then that will tell me the probability that if we randomly select a woman, she'll be between those. So that means I'm looking to find a proportion on the curve. So if we think back to our calculator functions, remember that the function in our calculator that will give us the proportion of the normal curve is the normal CDF function. And remember what it takes in. It takes in z-scores. All right? So what that means is that I'm going to need to find the z-scores for these values in order to be able to apply the normal CDF to those. All right, but I can do that. I know my mean, I know my standard deviation, so the z-score for 261 would just be 261 minus 270 all divided by 9, which gives me -1. And the z-score for 279, 279 minus 270 all divided by 9 is equal to 1. So that allows me to draw an accurate picture here on my normal curve. I can see that what I'm really interested in here is if I draw the standard normal curve that has z-scores along the axis here, what I'm really looking for is to discover the probability of selecting a woman whose gestation is between 261 and 279 days is the same as finding the proportion of the normal curve taken up in this region. All right, now if you remember our 68, 95, 99.7 rule, you can probably answer this right away. You remember that between -1 and 1 in terms of z-scores, you always get exactly 68% of your data. So really that is the answer. But let's go ahead and go through the motions of what we're doing when we use the calculator to give us our answer. So we're trying to figure out what is the probability that our x value falls between 261 and 279 days. So by this calculation of our z-scores, we're saying that answering this question is the same as answering the question of what's the probability that my z-score is between -1 and 1. But we know that this can be answered with normal CDF. So we just find the value for normal CDF between -1 and 1, and that is going to give me, like I expect, about 0.68. When we type that in the calculator, what we get exactly is 0.683. All right. So that's our probability. So what I want you to notice is that we started by saying, what are we being asked for? If we're being asked for a probability, then that means we need to know the proportion of the normal curve in the region. In order to get that, we need to put z-scores into normal CDF. So that means we needed to take our x values, our variable values, and convert them into z-scores. All right, so really that first step in the process was to use our z-score formula that we know, and then that gave us our z's, which allowed us to find the proportion of the normal curve. All right, so in part B it says, what is the probability that a randomly selected woman's gestation period is below 265 days? So again, just as a reminder, the mean is 270, the standard deviation is 9. All right, so again, what are they asking us for? They're asking us for the probability of being below 265 days. So this really follows the same pattern as the last problem, right? So what do we want to know? We want to know the probability, which means we need to know the proportion of the normal curve in the region we're interested in. So we know that the ticket to doing that is normal CDF. And what does normal CDF eat? It eats z-scores, right? All right, so I need to know the z-score for what I'm interested in, and in this case I only have one value. So my z-score for 265 is 265 minus the average of 270, all divided by 9, which is negative 0.556. All right, so let's draw a picture. Let's not get too far ahead of ourselves. So negative 0.556, puts me maybe right about there on the standard normal curve. And so it says we want the woman's gestation period to be below 265. So I know that I'm filling in that shaded area there. All right, so I'm trying to answer the question, what are the chances? What's the probability that x is below 265? Okay, so I'm starting off with this x value up here. But in order to use normal CDF, I turn it into a z-score. That's what we did right here. So that's the same as finding the chances that my z-score is below negative 0.556. But then that can be done by taking normal CDF. And remember, if we don't have a low value, if it just goes on, we just put in an extremely low value, like negative 1,000, and that'll do the trick. So the normal CDF, negative 1,000 up to negative 0.556. And so the probability of that is 0.289, so a 28.9% chance that if you randomly select a woman and her pregnancy, that pregnancy will have a length of less than 265 days. All right, lastly here it says, what is the length of gestation for the 90th percentile? The 90th percentile. So first, what are they asking us for? They want us to find the length of gestation, but the length of gestation, let's just understand right off the bat, is our variable value, right? It's the variable value. It's the x. That's what we want to know in the end. Okay? So this is our goal. Now, in order to figure this out, okay, I'm probably going to need to use one of my calculator functions. Okay? Well, normal CDF spits out a proportion of the normal curve. That's not what I'm being asked for. But inverse norm, it spits out z-scores, right? So an inverse norm will always tell you a z-score. So if I'm told a z-score, can I figure out my x value? Well, sure. Remember, we have a formula for this. If we know our z-score and we want to know our x, remember we have the formula, x is equal to the mean plus z times the standard deviation. We have that formula at our disposal. So if I can just figure out my z-score, then figuring out the length of gestation is as simple as just plugging all these values in, right? Because I know that my mean is 270, and I know that my standard deviation is 9. All right, so what do I need to put into inverse norm in order to get my z-score? I need to put in, remember it's very picky, the proportion of the normal curve to the left. It's always got to be to the left. Okay, so let's sketch a picture here. I'm interested in the 90th percentile and what value that happens at. So I'll make a little sketch of what about the 90th percentile would look like. Let's put it right about here. Oops, put it right about there. And fill this in. Remember the percentile, 90th percentile means 90% of the population is below you, so that's 0.9 to the left. So what this means is that I can figure out the z-score that I'm interested in here by asking inverse norm to give me the z-score when the proportion to the left is 0.9. So my approximate answer for the z-score is 1.282. So that tells me where I'm at on the curve along the x-axis, or along the axis here that shows my z-scores, but it doesn't give me the answer to the question. But that's what this formula is for. So now I've got the z, so I apply this formula to get the actual gestation length. So x is equal to 270 plus the z-score 1.282 times the standard deviation of 9. And when I put that in my calculator, I get about 281 and a half days. So on these problems involving the normal curve, we're typically going to either be using the normal CDF function or the inverse norm function as the key to getting to our solution. And the key to deciding which is the appropriate one is to say, what are they asking me to give as an answer in the end? If, like in this case, they're asking us to give a variable value as an answer, then inverse norm is your ticket. You find your z-score with inverse norm and then use this formula to find the variable value. If, like in this last one, they're asking for a probability or they're asking for the percentage, then we know that normal CDF is going to give that to us. And normal CDF needs us to tell it the z-score. And so in order for us to tell it the z-score, we first have to compute the z-score for whatever variable values are involved in the problem.